Today, on how it's made. Binoculars. Sparklers. Rubber boots. And circular saw blades. A pair of binoculars is essentially a handheld double telescope. Light rays from the object you're viewing enter the lenses on the far end, the objectives. This projects an image just behind those lenses, inside the binocular's housing. The smaller eyepiece lenses you peer through then magnify that image. The objectives are curved, causing the image to appear upside down. To turn it right side up, each binocular half needs a glass prism. Using UV light-activated glue, workers mount several prisms on steel plates that take them through a series of grinding and polishing steps. Protective paint prevents any dust from contaminating the pristine surface. Grinding with diamond dust removes mere tenths of a millimeter of glass. Polishing with an even finer abrasive removes another 1/100th of a millimeter. At the end of it all, the three sides are perfectly flat. This minimizes reflection, critical for making the glass see-through. To make each prism, they glue two pieces of glass together at 90 degrees. This special machine ensures the angle is precise. A shot of UV light dries the glue. The first piece of glass rotates the inverted image 90 degrees. The second rotates it another 90 degrees, completing the flip. Now for the objectives. These curved lenses have undergone the same grinding and polishing steps as the prisms. Now they go through a 9-stage computer-guided cleaning process. After inspecting the lenses, a technician glues two together. A double lens limits a type of distortion that causes fringes of color to appear around the image. It's critical to match them to each other perfectly. If the alignment's off by more than just 1/100th of a millimeter, the image will be poor. This alignment machine displays a dot representing the center of each lens, so it's just a matter of matching the dots. A 2-second shot of UV light dries the glue. Next, a technician loads mineral pellets into a vacuum chamber. Their exact formulation is a company secret. The pellets produce an anti-reflection lens coating that lets more light come through the lenses. Inside the vacuum chamber, a beam of electrons evaporates the pellets into microscopic particles that coat the lenses. It's time to begin assembling the binoculars. First, the objectives go into the housing, which is usually made of plastic, aluminum, or carbon. Workers clean the lenses with a few blasts of compressed nitrogen. Then secure them in place with threaded holding rings. Now a few drops of glue behind the objectives, where the prisms will go. Another blast of nitrogen to remove any dust. Then they insert the prisms. This optical machine aligns the focal points of the prism and its corresponding objective. Then some more glue to lock in the positioning, and a blast of UV light to dry the glue. Now they silicone the objectives and prisms to the housing's middle section. Silicone creates an airtight and waterproof seal. This holding mechanism presses the parts together while workers drive in the screws. Onto the opposite end of the middle section go the oculars, the smaller lenses through which you look. Those also attach with threaded holding rings. Now, through a valve on each side, a machine sucks air from the housing and injects nitrogen gas. Nitrogen prevents the lenses from fogging up. A day after filling, they recheck the nitrogen pressure to make sure there's no leak. This factory puts all the binoculars it produces through rigorous testing, subjecting them to prolonged vibration, water pressure, extreme heat, freezing temperatures, and other trying conditions. After every test, inspectors make sure everything still works perfectly, both mechanically and optically. Sparklers have sizzled on the party scene for decades, adding pyrotechnical glitter to weddings and birthday celebrations. They evolved from more traditional fireworks and are the only kind that the consumer can handle when lit. Lighting one definitely means excitement is in the air. The splash of flash can last a minute or more, depending on the length of the sparkler. They start with steel wires that are about 48 centimeters long. They load bundles of them into the slots of a sorting machine. The machine vibrates, and the wires fall in single file into smaller openings. The operator then moves a spring-loaded wooden rack into position. It opens like the bellows of an accordion. The operator rocks the sorting machine overhead, and the wires drop into the slits of the rack, perfectly aligned. After 300 sparkler wires have fallen into position, the operator pulls a handle to close the rack. Now clamped in the accordion-style rack, the wires are ready to move on to the next station. Wires for parade sparklers are much longer, 91 centimeters in fact, which means they're heavier than ordinary sparklers. The operator loads each of these wires manually into a rack that's larger and sturdier than the last one. This system of loading is a lot more time-consuming, but parade sparklers are worth the extra trouble because they'll have a longer burn time, up to 4 minutes. Next, an operator loads boric acid and barium nitrate into a big mixing tank. The barium nitrate is an oxidizer and will help the sparkler burn. The boric acid is a neutralizer. He adds water and mixes in cornstarch. It will bind all the ingredients together. Next, he pours in some very fine iron filings. These bits of iron will give the sparklers their gold color. The operator then suits up in protective gear and closes the door. He's the only one allowed inside to load the sparkler's most volatile ingredient, aluminum powder. Once mixed into the wet slurry, the powder is virtually harmless, and they don't need to take as many safety precautions. Chain conveyors now move the rack of sparkler wires into position. An elevator lifts up the tank of the sparkler slurry to dip the wires in it. The next rack of wires then moves forward for dipping. 286 racks of wires move through this dipping station every hour and 45 minutes. They go through a second dipping station for one more coating. The two coatings double the diameter of the wires. After each dip, wires ride an overhead rail through an oven to bake the sparkler slurry until it's hard. An inspector then examines each sparkler. She checks for cracks and defects. Any wire that's flawed will be rejected because these sparklers have to outshine the competition. It takes her about 3 minutes to examine the 300 sparklers on a rack. They check the diameter of each sparkler by sliding it through a template, and they bend it to check its integrity. The sparklers have been stored for a week prior to packaging to allow them to cure. And now, they're ready for a party, and they're sure to be the center of attention. Wellington boots, billy boots, galoshes, by any name, rubber rain boots owe their existence to a 19th century American, Charles Goodyear. He invented the vulcanization process, a way to keep natural rubber from deteriorating. Nowadays, rain boots are made from a synthetic material called thermoplastic rubber, or TPR. They're functional, even fashionable. Making rubber boots begins with spools of polyester yarn for their lining. A colored spool adds a thin line of color to indicate the foot size of the lining. A computer-programmed machine crochets the yarn with 242 needles. As we can see in slow motion, each gate opens completely, then closes on the yarn. The needle rotates 750 times per second. They can program the machine to make linings for any size of boot. For quality control, workers spot check a few linings from every batch. Now the action moves to this automated injection molding machine with 6 stations. Each one produces a pair of boots. Workers carefully roll a pair of linings onto each station's foot form, called the last. These lasts will create the space inside the boot for the lower leg and foot. A 5-part boot mold closes around the foot last, then a high-pressure injection screw pushes in melted synthetic rubber, first in the soles, then in the upper boot. The company lab regularly tests samples of the synthetic rubber pellets that feed the injection machine to make sure they melt and flow well. The lab technician pours in some pellets, melts them, then pushes in a piston to extrude the molten rubber. The machine measures what's called the melt flow index. Back on the factory floor, a large suction hose feeds rubber pellets to the injectors, black for the boot body, red for the soles. And at this factory, nothing goes to waste. It recycles rubber leftovers or rejects of all colors into a batch of black rubber. The suction hose sends the pellets into a hopper, which feeds the barrel of the injection unit. The heating bands inside the barrels melt the pellets at 200 degrees Celsius. Then, at the precise moment the mold arrives, the injector shoots in the molten rubber. Giant clamps apply pressure for about 10 seconds, then release. A hydraulic cylinder pushes up the last, helping to extract the boots. Then it's quickly on with new linings for the next pair. Total molding time, just 30 seconds. The boots cool for 45 minutes, then head off to packaging. They make one stop along the way at the pad printing machine to get the company's logo. Elsewhere in the factory, a seamstress carefully constructs a patterned boot lining. The factory crochets white linings in a continuous roll, then has another company print on the design. The trickiest part is shaping the toe, because she has to curve and cut the material at the same time. For these patterned boots, the machine injects a transparent synthetic rubber into the mold so that the printed lining will show through. The mirror-finished surface of the mold cavity produces a high-gloss boot. The printed boot requires more work and costlier materials, and is therefore more expensive. After the molding, for example, it has to go to the trimming station. There, a worker shaves off excess material from the top of the boot. Then he sews on a fabric binding to sandwich the lining. The factory randomly selects a boot from each batch and puts it through a battery of tests on this flex machine. It bends the boot in various ways, some 300,000 times, ensuring these rain boots can walk the walk. When a construction site is buzzing with activity, it's usually the sound of the circular saw. Its spinning teeth can take a bite out of any job in seconds. There are many claims to the invention of the circular saw, but there's no doubt that when its design was perfected in the last century, it revolutionized woodworking. With a circular saw, you can give odd jobs a whirl, and when the sawdust settles, you may have discovered your inner handyman. To make a circular saw blade, a laser burns into a sheet of steel to cut out jagged discs in the basic shape of a circular saw blade. They feed each disc to rollers that press grooves onto both sides. These grooves are tensioning rings that will keep the blade from vibrating while cutting. Without these grooves, the circular blade wouldn't cut straight. At the next station, the assembler measures sags and buckles before feeding the discs to a machine that rolls them flat like a pie crust. A grinding wheel polishes the blade. And then they load barrels of the discs into an oven to bake until they're very hard. This will take about 24 hours. Meanwhile, carbide tips for the blade's teeth funnel past a laser that confirms they're properly positioned for the next step. A robot then picks up one tip at a time and delivers it to nozzles. The nozzles pump a paste called flux onto it. Another robot places a piece of solder metal on the flux. The next robot delivers the tips to the saw blade body. Elements melt the solder metal and flux to fuse the carbide tips to the teeth. It's a technique called brazing. Teeth with carbide tips last longer without losing their sharpness. Circular blades for sawmills have a larger and different design. They brush flux around a side hole and then place soldering metal on an elongated carbide tooth. They braze the tooth to the flux-coated hole and install several more of these carbide side teeth. The side teeth will enable this sawmill blade to tear through big logs. The smaller circular saw blade now spins on an axle while a spray nozzle sandblasts it. The sandblasting cleans the surface and gives the blade a brushed texture. A mechanical finger now moves one of the blade's teeth into position for sharpening. A grinding wheel tapers each tooth. A different wheel moves in and grinds the outside diameter of the blade. The geometric angle of the grinding can vary depending on the type of blade being made. The grinding wheel then hones the face of each tooth to give it a sharper edge. Next, a straightening specialist pounds out any remaining bumps in the blade and double-checks it with a straight-edge tool. He wipes off any smudges and then holds the blade to the light and examines it to confirm that it has no flaws. A laser then etches the company insignia onto the blade. And now this circular saw blade is ready for its close-up. A camera focuses on the teeth and sends the picture to a computer. It analyzes the cutting angle and the clearance of each tooth to make sure each one measures up. The result is circular saw blades that should be able to keep their edge on the job.